Okay, in this video we're going to be talking about how to automate some of your experiments. You might have a setup and you just want to run it multiple times with a bunch of different parameters. And so I'm going to show you guys how to do that in an automated fashion and in a clear way so that everybody can see how it's done and how you can easily recreate it yourself. So first things first, you should have the whole repository set up. And you can see the other videos for that. And all the work we're going to be doing is going to be in the multiple_simulations.hoc file. That's an excellent place to just kind of add random procedures that are all encapsulated within themselves, and then it doesn't mess around with things, so it's kind of a hodgepodge of here's things or experiments that we could do, and just so they're all there and documented. So actually, if I went over to a wiki page, you should see on the side that there is a multiple_simulations.hoc wiki page, and that actually has a list of all the current experiments, so to say, and a little bit about what they do. So when you do create a new one, which you can feel free to, make sure you mark your changes and update the documentation for it. Other key things before we start diving in, if you go on to the neuron.yale.edu site, you can go to the programmer's reference and make sure you're in the HOC documentation, not the neuron documentation. But this will be useful for if you're looking for like environment variables from HOC or from neuron specifically, whether it's like the time step or those kind of variables. You can search for those kind of things, and they will be there. So that's how you can kind of find some of those things that might not be explicitly easy to copy and paste from other pieces of code. So for this example, we're going to look at, so we're in the multiple_simulations.hoc. We're going to look at this find min frequency procedure. So obviously to define a procedure, you just put proc and then the name of whatever your method is, and then some parentheses. You can open your curly braces and you can define local variables. These ones are, so normally when you define a variable in HOC, all of that variable exists in the entire environment. So defining it as local means that once we are out of the scope of this procedure, those variables are destroyed, which is just good memory management. And it also means you won't have conflicts later on with variable names, which you don't want to do. So I recommend using locals where you can. From there, you should document what your experiment is going to do. So this one, it takes the current setup and tries to find the minimum frequency at which block can still occur, and the search space will be a range of frequencies from 0 to 10 kilohertz. So there's a couple preconditions in there that, I kind of set it so that it's specifically 0 to 10 kilohertz, but I kind of know that it's going to lie somewhere in there already, so I can make those kinds of assumptions. Optionally, we can pass an argument. To get arguments, use the num_args to check how many there are. And so I'm checking if there's more than one. And then to read the argument, you use the cache symbol followed by a number. And that number is the index of the argument, starting with 1. So if there was one argument passed, I know num_arg is going to return a value of 1, which is greater than 0. And so if they passed 100, or we'll say 500 for this case, $1 will be 500, because that's going to be the thing. If I passed another parameter, I could put $2 or $3 for more parameters. And so that's how you can kind of get a variable number of parameters. You just kind of check how many there are, and then you can set it. From there, I set up some initial variables, so my search boundaries, and then I begin my search. So as you can kind of see, this is kind of some standard. If you see stuff being, when you're doing a beginning search and you're checking if stuff is greater than the resolution and you're dividing by 2 each time, we can pretty well assume this is going to be a binary search through the frequency space. But from there, we pick a frequency by dividing the search space by 2 and picking the middle. And it's always good to give sufficient amount of output as you're going through. That way you can always be sure where you are while you're running your simulation, because otherwise you might end up with a simulation that runs for a while and you don't know how far you are. And maybe it takes a day, maybe it takes 10 days, and you want to know how long that's going to take. So don't be afraid to give extra output. From there, we have the waveform select. And so this one we kind of have to dive a little bit into how this repository handles the set of electrodes that are given with the GUI. So in the previous video, we had talked a little bit about custom electrode setups. In this particular procedure, we're going to dive a bit into the actual electrodes that are used with the GUI. And so the key thing is it uses this wave select array. And so if you go over to the waveform selection.hoc file, we can scroll through it. In fact, it might just be easier to do this and search through the file. And so we can see at the beginning it's selection flags to pick what type of waveform it is. And so we can set it as a square wave, a sine wave, a triangle wave. This is the sine ramp. And so you can see, if you remember, when we open up Neuron, it starts with it automatically picks a sine wave, and we can see that it's initialized that way, as a 1 being that's the one that's chosen and a 0 being all the others. And so this, we're going to check if it's a square wave, and if it's a square wave, we can call this set square wave frequency, and we could probably search for that method and look at it. The other thing to note is that this frequency variable, if we went over to the sine waveform.hoc, which kind of sets up the sine electrodes, so the sine waves, what we can do is we can look for that frequency variable, and we can see that so this is the GUI, because we can see it's calling all these like X value and X panel methods which are used for the GUI. And so we can see it uses this frequency variable, and if we keep going through, we can see that the sine clamps, which are the kind of the models for the electrode, we can see that that frequency is set by the freq variable, the FREQ. And so by setting it in this way, what we have here is, as soon as we set this variable, we've set it for sine waves, and as soon as if we happen to have a square wave instead, then we just have to make sure that we call that variable. Obviously this is pretty complex and we had to dive into a whole bunch of stuff, so that's why using the custom electrode setup can be a lot easier than trying to have to dig through all of this if you don't already know exactly how to use it. So we've picked a frequency in our search space, and obviously if we're trying to find the minimum frequency for block, then from there I'm going to call the find threshold function. So if you remember, when we dive through the threshold finder, we have a whole list of parameters, so we can search for that function and find it. And so functions will return a value. So unlike the procs, which just run a series of commands, the funcs will return a value. In this case, it's going to return the block threshold. And we're going to pass it a whole bunch of parameters, and so I can set the bounds of the search, the threshold for the AP counter, the actual potential counter, the stim, the test pulse parameters are pretty standard. You pretty much always wait 50 milliseconds, and you do a 10 nanoamp pulse for 0.1 milliseconds. Those are pretty standard. that means because there's a 10 millisecond delay on our electrode, that means we wait 40 milliseconds before we give a test pulse. And that's pretty standard. We can look at the sodium and potassium gates during block, and we can see that they pretty much plateau at about 40 milliseconds. So from there, I can also put things like the resolution. And so in this case, we don't particularly need a high resolution. We're just looking to see if it blocks, not how precise we can find the block threshold. And so from there, the cool thing with this fine threshold is that if I start going through it, and this is something that you'll need to kind of do if you're running, other types of simulations where you're just picking out a couple things and you're not actually going through everything, and you're not using like automated stuff that already does all your trials for you. You need to use what is called the run command. So the run method, which if you went through the NEURON documentation, you would see when you call this, it will run the simulation from the beginning to the end. And that ending is defined by the t-stop, which I don't think I define in this file, but if I went back over here, I can find it for sure. T-stop. So you can see in this method, I can't remember exactly what it's for, but setting this t-stop variable allows me to set the maximum time for the simulation. And so combining those two, so if I combine how long I want to run the simulation for, and then I call run, it's going to run the simulation exactly that long. And then from there I could, increase it and do other things. But so this one I didn't need to do that because I'm automatically using my fine threshold code that I've already written. And then from there I'm checking if a block threshold was found. And then from there I'm, continuing the binary search where we then change our search space to either the bottom half or the top half, and we keep going down until we reach the resolution. And so every time it's going to iterate through, I'm going to know exactly where I am, and then the fine threshold has its own set of output that it's doing, so I'm always knowing where I'm at. And then from there we print the minimum frequency for block, and then this is done. So that's one example of what you could do, and you could easily, write something similar for whatever it is you're trying to do. Other things to note, some of the other ones, if they're a little newer, they use the custom electrode configurations, which are obviously, they're a lot easier, as in they don't have to have you understand all of this extra code that we haven't gone through yet. So for these ones, you just set it up. The key things here, so this one actually looks at measuring some action potentials using the action potential counters, which are a very useful kind of set of code for doing multiple simulations and doing various runs. So before we get into that, the fine threshold, the thresh finder, that has it has the test pulses, and that is actually already initialized as soon as we start up NEURON and as soon as we load up our repository, which means if we're not doing something that's calculating the threshold, block threshold, we need to turn this off. Or you can utilize it for your own purposes by using the setStim method with whatever parameters you feel necessary. But if you're not using the test pulses, you need to make sure you turn them off by using setStim with 3 zeros as the parameters. That just turns off the amplitude, duration, and the delay. So it just turns it off all the way. If you forget to do that, then you're going to have an extra action potential in your trials, and that'll mess up your data. So after you've turned that off, then we can start to look a little bit at the action potential counters. So you always want to reset them before a run, and then what we can do is we can get the count of either the left side or the right side of the axon. So if I go down and I find, where is the APC count controller right there. So we have a distal and a proximal AP counter. And so they're both set. One is set at one end of the axon, one set at the other. And from there, what we can do is we can set them up using the set the threshold, and we can reset them, and we can reset their counts. But the key thing here is the get count and get times method. What they do is you can send a 0 or a 1, 0 being the left side and 1 being the right side of the axon. And from there, what we can do is we can return the number of action potentials that were seen at that side. So if you reset it before you run, now when we get to this point and we're calling this APC get count 0, we're going to get the number of action potentials that were on the left side of this run of the axon. They were on the left side during this entire run. And that's really powerful if you're looking at, let's say you're looking at onset, or you're looking at some other phenomena where you're looking particularly at how many action potentials are getting through. That's going to be really powerful. And then just remember to clean up your simulation environment when you're done using custom electrodes. So yeah, those are all kind of a lot of helpful tools to hopefully get you through setting up your own automated testing. And I think from here what we can do is we can start looking at how to automate this even more using some parallel computing and Python. So hopefully that was useful, and we'll see you guys in the next video.